Good morning. Good morning. Good morning. All right, let's get started. Talking about matrices, eigenvalues, eigenvectors, all sorts of jazz. Right pen, sure. Good. Okay. All right, so talking about most of our examples are going to be for 2x2 matrices, but we will do some 3x3s. But most of the stuff we're usually doing is 2x2. So let's start off with a general 2x2 matrix. So for the 2x2 matrix, usually matrices get capital letter names. So A equal to the general A, B, C, D. Two things. Thing one, the determinant of A is written as DET parentheses A, and it's equal to the product of the diagonals minus the product of the off diagonals. So A times D minus B times C. For 3x3s, it's a little bit more complicated, but we'll do an example in a minute. And then the inverse of A is written as A to the -1 power, but we say A inverse. Don't say A to the -1, say A inverse. And that's going to be equal to 1 divided by the determinant of A times what I always think about for the rest of this is you're taking your original matrix and you're interchanging the diagonal things. So A and D switch places. And the off diagonal things, B and C, you change their signs. So you have the negative of whatever B was and the negative of whatever C was. A couple notes. Note, if the determinant of A is equal to 0, then we won't have an inverse because you have to divide by the determinant. You can't divide by 0. So if the determinant of A is equal to 0, then A inverse won't exist for that particular A. And if that's the case, we say that A is we say that A is singular if A inverse doesn't exist. Similarly, we say A is non-singular if A inverse does exist. Or another way of saying that, or if the determinant of A does not equal to 0. The way I often think about this terminology here is that if your matrix is non-singular, it's not single. It has a partner, and its partner is its inverse. Whereas if a matrix is singular, it's all by itself. It does not have an inverse. That's how I've made myself make it work in my brain. Let's look at an example here. So let's say we have the matrix A equal to 7, 3, 2, 5. So let's ask the question, does A inverse exist? And if so, find it. So this question is first asking us to determine whether or not the matrix is invertible. So to answer this question, you don't want to start finding the inverse. You want to just say, what's the determinant? So does A inverse exist? Well, the determinant of A is equal to 7 times 5 minus 3 times 2, which is 35 minus 6, which is 29, which is certainly not 0. So yeah, the inverse exists. And we're going to find it by just throwing this matrix into that formula. So A inverse in this case is going to be 1 over 29, 1 over the determinant that we just found. And then we're going to switch the 7 and 5. And the 3 and 2, they change the sign. So you have a -3 there and a -2 there. Something that I haven't said yet, but that I should say is the thing that's special about an inverse is that when you multiply a matrix by its inverse, you end up with the identity matrix. So just as a kind of quick note here, note that A times A inverse is equal to the identity matrix. Let's actually check that out and see if that works. So in this case here, we have the matrix 7, 3, 2, 5. Multiply by, I don't want to actually multiply this 129 through. You can, but I don't think it looks any nicer. I'm going to say it's times 129 times the matrix 5, -3, -2, 7. The nice thing about constants, so unlike matrices where the order matters and you have to keep everything in order, for constants, you can move them wherever you want to, or constants or scalars, if you want to call them scalars. So we can rewrite this as 129th times the matrix 7, 3, 2, 5 times the matrix 5, -3, -2, 7. And I'm going to wait to multiply the 129 through until the very end. So then you've got 129th out in front, and then we're going to do the matrix multiplication. So I'm going to have 7 times 5 plus 3 times -2, which is 35 minus 6, which is 29. And then we're going to get 7 times -3 plus 3 times 7, which is 21 minus 21. And you have 2 times 5 minus 5 times 2, which is 10 minus 10. And then you have -6 plus 35, which is 29. And look, 129 times this matrix is exactly the 2 by 2 identity matrix, 1, 0. So if someone ever says matrices are inverses of each other, like for example, if I just said A and B are inverses, then the first thing I typically would write down to help myself kind of do whatever the problem's asking me to do is to note that that means A times B is equal to whatever the appropriately sized identity matrix is. And also, this is atypical, it's also true that B times A is also equal to the identity matrix. So most of the time, matrix multiplication is not commutative, but a matrix multiplied by its own inverse, that matrix multiplication is commutative. You can do it either order, and it'll end up still being the identity matrix, which is cool. Okay, let's do a couple more examples, then we'll talk about a couple 3 by 3 things. We can keep things in order here. Let's look at this next matrix. Let's say here's the matrix B equal to 4, 10, 6, 15. Is B invertible? Well, let's find out. Is B invertible? The determinant of B is equal to 4 times 15 minus 10 times 6. And just to say it again, when I'm doing the determinant, I'm really just thinking multiplying that diagonal minus that off diagonal multiplication. So it's going to be 60 minus 60, which is 0. So that means B is not invertible. So B is not invertible. Or alternatively, we could say B is singular. I shouldn't say that. That's not true. So really you can take the determinant of any square matrix, and there's a process for doing that for larger and larger matrices. But the biggest we'll talk about in this class is a 3 by 3. There is a way to do it for a 4 by 4 or 5 by 5, larger, 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 but it gets more complicated. But for a 3 by 3 matrix, there's kind of a special trick, for lack of a better way of saying it. So to find the determinant of a 3 by 3 matrix, determinant of a 3 by 3 matrix. Let's say A equal to the matrix A, B, C, D, E, F, G, H, I. So here's what we do. To find the determinant of a 3 by 3 matrix, we duplicate the first two. You can actually do first two columns or rows, but we usually do it as columns. The first two columns of A. Sorry, I lost my voice. Of A, just to the right of A. So all we're going to do is we're going to write the same matrix down, and then we're going to add another column of A, D, G, and B, E, H. So we've got this A, B, C, D, E, F, G, H, I. And then we have the column A, B, G, B, E, H. And then what we're going to do is we're then going to add the rightward diagonal products and subtract the leftward ones. The leftward diagonal products. Here's what we usually do. We usually draw it like this. We say, okay, we're going to do this product plus this product plus this product. So the determinant of A is going to equal A times E times I plus B times F times G plus C times D times H minus, and I like to just use one big parentheses, the leftward downward diagonal product. So C times D times G minus A times F times H minus B times D times I. I know I'm saying minus and I'm writing a plus sign because it's minus all of that added together. But really, I mean, you shouldn't memorize like these letters or anything. You should be like, oh yeah, it's just these downward rightward ones added together minus these downward leftward ones. So let's look at an example. It's a little bit more, I think, helpful. So let's say we have the following actual 3 by 3 matrix. Really, you can make up anything. Let's say we have the matrix A equal to 1, 0, 3, 2, 7, 9, 0, 2, 1. So then the question is A invertible? Or I could phrase it as, is A non-singular? Okay, so let's find the determinant of A. So the determinant of A, we're going to find by doing, so I wouldn't recommend like writing this matrix again. There's no reason to write the matrix twice. Just take this matrix you've already got and rewrite the columns right here. So 1, 2, 0, 0, 7, 2. So my determinant is going to be 1 times 7 times 1 plus 0 times 9 times 0. I really should just write 0, but I'll write the whole thing. Plus 3 times 2 times 2 minus 3 times 7 times 0 1 times 9 times 2, 0 times 2 times 1. I'm doing too much work here. If you have 0 times, you should stop writing anything. You should write 0. Let's see what we've got here. So we've got 7 plus 0 plus 3 times 4 is 12 minus 0 plus 9 times 2 is 18 plus 0. So we end up having 19 minus 18, which is 1, which is not 0. So is A invertible? Yes. A is invertible. A is non-singular. Yeah.
Equal to 0.
If what's equal to 0?
What do we call that?
What do we call that?
I don't know, I just lost.
It's called the determinant. So if the determinant is equal to 0,
Then it's not.
correct, then the matrix is not invertible, the matrix is singular. Those two things mean the same thing.
And the only value is 0.
Right. If it's equal to 0, it is not invertible, it is singular. If it's not equal to 0, it is invertible, it is non-singular. Right. And it can be any non-zero. So the reason we talk about the inverse sometimes is because it helps us solve matrix equations. For example, if we wanted to solve the system of equations 2x plus y equal to 7 and x plus 3y equal to 4, well, we could, solve for x and then plug back into the other equation and solve for y and then plug back into the other equation and solve for x again. But it's faster to write it as a matrix equation. So we can write this as the coefficient matrix 2, 1, 1, 3. Excuse me. The first column is the coefficients of x. The second column is the coefficients of y. The first row is the coefficients in the first equation. The second row is the coefficients in the second equation. Times x, y equals 7, 4. And I want to really stress here, this equation, and sorry, I should say, this system of equations and this system of equations are the same. They represent the same exact thing. If you multiply this out, this is 2 times x plus 1 times y equals 7. This is 1 times x plus 3 times y equals 4. So this matrix equation and this system of equations are the same systems of equations. But then we can solve this system by using the inverse matrix. So what we're going to do is we're going to multiply both sides on the left by the inverse of this matrix 2, 1, 1, 3. So if we call this A, we typically call this the vector X, and this is B. And I should point out some terminology here. When you have a matrix that is like a 2x1 matrix or a 3x1 matrix, or essentially it's a matrix that only has one column, we often just call that a vector. It's still a matrix as well, but it gets referred to as a vector frequently. So just familiarize yourself with that and get comfortable with that. So what we're going to do is we're going to multiply both sides by A inverse. In fact, let's just do it without writing down the matrix for a second. So if A times X equal to B, we're going to multiply both sides on the left by A inverse. So A inverse times A times X equals A inverse times B. And for whatever reason, when they're vectors, we like to write them with little arrows over them. That's just kind of typical notation. But then you can rearrange the left-hand side and write it as A inverse times A times X equal to A inverse times B. And then A inverse times A, that's the whole thing about being inverses. When you multiply them together, you get the identity matrix. So this becomes the identity matrix times X equal to A inverse times B. But then the identity matrix times anything is just whatever the anything is. So this becomes the X, the thing we're trying to solve for, is equal to A inverse times B. So what that means here is we can get a solution by just multiplying both sides by the inverse and getting xy equal to, let's see, A inverse is going to be 1 over the determinant, which is 6 minus 1, so 5. And then A inverse is going to be, well, I misspoke there. The rest of A inverse, because the 1/5 is part of A inverse, right? The whole thing I'm about to write down is A inverse. So 1/5, and then we're switching the 2 and the 3. And the ones are changing their signs both to -1. So right there, that is your A inverse times the 7/4 that was still on the other side. So all I did was I took this equation, I multiplied both sides on the left by A inverse. I didn't write it over here because we knew that A inverse times A was going to be the identity matrix. So then let's see what happens. If we multiply this out, we get 1/5 times 3 times 7 plus -1 times 4 is 21 minus 4, which is 17. And -1 times 7 plus 2 times 4 is -7 plus 8, which is 1. So our solution here is x is equal to 17/5 and y is equal to 1/5. And if you plug those values back into your original equations, it really does work. 2 times 17/5 plus 1/5 is 34/5 plus 1/5, which is 35/5, which is 7. Check. And 17/5 plus 3 times 1/5 is 17/5 plus 3/5, which is 20/5, which is 4. Check. So this really does work. Okay. So why don't you all try solving this next one? I want you all to solve the following. Solve the equation. And we're going to use x1 and x2 instead of x and y. 2x1 plus 3x2 equal to 5. x1 minus 5x2 equal to 9. By writing it as the matrix 2, 3, 1, -5 times xy equal to 5, 9. And then you should be able to solve for xy equal to your A inverse. This is just A, James, times whatever your B was. So your job is twofold. Your job is to find A inverse for this matrix A, and then multiply your A inverse by the vector 5, 9. Try that on for size. So there's your inverse matrix. It's, you either say 1 over -13 or -1/13. And then times the 2 by 2 matrix, -5, -3, -1, +2. And if we do the multiplication, we're going to get negative, It's always fun to write this out. So we get negative 1/13 times negative 5 times 5 plus negative 3 times 9 is negative 25 minus 27, which is negative 52. And negative 5 plus 18 is 13. Now, it looks like the numbers work out pretty nicely here. Negative 1/13 times negative 52 is positive 4. I always remember that a deck of cards has 52 cards in it, and each suit has 13 cards in each suit. So 52 divided by 13 should be 4, or 4 times 13 should be 52. And then negative 1/13 times 13 is just negative 1. So in this problem, our solution is x1 equals 4 and x2 equals negative 1. So these two systems of equations that we just looked at have one solution, an x and a y, or an x1 and an x2, which we can imagine is where these two lines intersect. So if you graphed the two lines, 2x plus y equals 7 and x plus 3y equals 4, you would have two lines and they would intersect at that point, 17/5, comma 1/5. And similarly here, these two lines, I'm going to think of this as 2x plus 3y equal to 5 and x plus minus 5y equal to 9. Those two lines, if we graph them, would intersect in the point x equal to 4 and y equal to negative 1. But not every set of two lines intersects. So what happens if the matrix A is not invertible? And we can't just multiply both sides by the inverse. Well, two things can happen. There are two possibilities. One, the system has no solutions. Which I think of as the lines being parallel. They never intersect, so there's no solution to both equations at once. Or the system has infinite solutions. What I like to think of here is both of the equations actually are the same line, and so they completely overlap everywhere. So let's look at two things that represent this. So let's look at this first example here. Let's say our system of equations was 2x plus y equal to 7 and 2x plus y equal to 5. Are these lines the same as each other? Definitely not, right? If you solve for y here, this is y equals negative 2x plus 7. This is y equals negative 2x plus 5. Those are lines that have the same slope and different y-intercepts. These lines are parallel. Something like that. And this system of equations has no solutions. And I'll point out that the matrix A, which would be 2, 1, 2, 1, definitely is not invertible. Its determinant is certainly 0. So sometimes when the determinant is 0 or the matrix is not invertible, you don't get any solutions. But on the other hand, you could have similar situation, but now our example is, say, the equations 2x plus y equal to 7 and negative 4x minus 2y equal to negative 14. Here, the equation looks like this. It's 2, 1, negative 4, negative 2 times xy equal to 7, negative 14. But here, the determinant's still 0. I shouldn't say but, right? Here, the determinant of your matrix A is negative 4 minus negative 4, which is 0. And in this example, we have an infinite number of solutions. Because both this line and this line are the same line. And the way I kind of like to think about this is if you take this first equation and you multiply the entire equation by whatever the right number is, in this case, -2, you multiply that entire equation by -2, you exactly get the second equation. -4x minus 2y equal to -14. So those equations really are the same equation, meaning that every point on that line is a solution. So here, infinite number of solutions, and the solutions are all points on the line 2x plus y equal to 7. So if you want to write your solutions in kind of a vectory sort of way, I would say, how would I write this? Yeah, I would be maybe mildly annoying about it and say x equals r, because we like to do this weird kind of parameterization thing, and then solving for y equals 7 minus 2x, so y equals 7 minus 2r. So my solutions here are x, y equal to, well, x is r, and y is 7 minus 2r. And then for some God knows why reason, we like to break this up into the r parts and the not r parts. So we can write our solutions like that. Basically, there's your y-intercept at 0, 7, and here's the slope of your line being -2. That's kind of neat. It's kind of annoying. I wouldn't stress too much about this. The important thing to notice here is not so much how to write these solutions, it's that we have an infinite number of solutions, which are just all points on the line. You could just have easily have said, my solutions are all points on, I already wrote it. Solutions are all points on the line 2x plus y equals 7. I think that's just as good an answer. Okay, time is it? All right, we're out of time. Yeah, we should probably do that. Let's do that. We're about to get to eigenvalues. We're getting there. We're almost there. I just want to do one more thing kind of in this context, because I definitely remember seeing some problems on that practice midterm 3, whatever thing that he said, were for the final. And there were some questions. It was like, find values so that this system has no solutions or one solution, infinite number of solutions. So let's look at an example like that. So let's say we've got the following system of equations. We want to find constants A and B so that the system ax plus 3y equal to 5 and 4x plus 6y equal to b has, and we'll do each of the 3 possible cases, no solutions. Okay, so to have no solution or infinite solution, the determinant of the matrix has to be 0. So we need the determinant of the coefficient matrix A, 3, 4, 6. We need that to equal 0. So that means we need A times 6 minus 3 times 4 equals 0. So that means we need A equal to 2. But we're not quite done because we want to have no solutions. So we want these lines to be parallel and not the same. So if A is 2, we have 2x plus 3y equal to 5, and we have 4x plus 6y equal to b. So for these lines to not be the same, what's the only value of b that's a problem? Well, what if I was going to multiply this equation by a number to get this equation, what number would I be multiplying the first equation by? 2. So 2 times 2 is 4, 2 times 3 is 6, and 2 times 5 is 10. So 10 is the problem. Right? I don't want 10 in this case, because if it were 10, I'd have an infinite number of solutions because they'd be the same line. So A has to be 2, and B has to be anything but 10 So you can pick 9 or 7 or 70 million or whatever you like. Okay, and then I think we've already answered the second question, which is if you want an infinite number of solutions, but we still need A equal to 2 because the determinant of the system has to be 0. And then we also need B equal to 10. So that those two equations are representative of the same line. Finally, to get exactly one solution, we need the matrix to be invertible. So A can be anything except for 2. We need determinant of the matrix to not be 0. So we need A to not be equal to 2. And that's kind of it, because it doesn't really matter what B is. If the matrix is invertible, you can always find the solution, regardless of whether B is 10 or 5 or a million or whatever. Cool. Okay. All right, so let's, oh yeah, there's one other thing we should talk about. So something that I want to just point out is that, let me write this down. When we multiply a matrix by a vector, we get another vector. I'm specifically thinking of a 2 by 2 matrix multiplied by a 2 by 1 vector, but it's true for larger things as well. Usually with a different direction and magnitude. For example, if your matrix is 1, 3, 2, 5, and your vector is the vector, let's just start with 1, 0. A times that vector, which is equal to 1, 3, 2, 5 times the vector 1, 0, is going to give me, let's see, 1 times 1 plus 3 times 0, and 2 times 1 plus 5 times 0. So what we're doing here is we're taking our initial vector, that's 1, 0, and I know it's kind of hard to see exactly that, but let me draw it again. And we're ending up with a vector that's 1, 2. So the matrix A has changed both the direction and the magnitude of the vector it multiplied by. And that is typical. Usually when you multiply a matrix by a vector, you get a vector that's pointing in a different direction and its length has changed. However, there are some matrices that keep one of those things the same. If you want to not change the length, well, then you're rotating the matrix, the vector, sorry. So, for example, this matrix, A equal to, what do I want? Sure, fine. Is that really what I want? So I'm just thinking about what I really want here. Sure. We could do this. We could do square root of 3 over 2, 1/2, negative 1/2, square root of 3 over 2. This is a rotation matrix. It's going to change the direction the vector points in, but it's not going to change the length of the vector. So for example, if you were to multiply this matrix by the same vector v, so if you take A times the vector v from above, where v is still the vector 1, 0, we're going to end up getting this matrix, root 3 over 2, 1/2, negative 1/2, root 3 over 2, times the vector 1, 0, which is going to give us root 3 over 2 plus 0, and then negative 1/2 plus 0. And if you look at what's happened, our vector v, and I'm just going to draw this up here because I have room up here. our vector v, which started off pointing in the direction of 1, 0, now is pointing in the direction of √3/2, comma, -1/2, which I'll point out, √3/2 is approximately -0.86. -1/2 is -0.5. Sorry, positive 0.86. Don't be crazy, James. So what we've done is we've gone down here, pointing like that way. This vector, a times v, still has the same length of 1. Because if you look at these values here, if you find the magnitude of this vector, in fact, let's find it. The magnitude of the vector a times v is the square root of the square root of 3/2 squared plus -1/2 squared, which is the square root of 3/4 plus 1/4, which is the square root of 1, which is 1. This matrix didn't change the length of the vector because this matrix is special. This is an example of a rotation matrix. You might notice that these values, you might not, but you might notice that these values look like the values you get when you take cosines and sines of a certain angle. And it is. More generally, because I think it's worth knowing, and I know there's a few homework problems about this. The matrix, I'm going to give it the name R sub theta equal to cosine theta, negative sine theta, sine theta, cosine theta, is the counterclockwise rotation matrix by the angle theta. So if you wanted to rotate your vector 90 degrees, so if we want to rotate a vector by 90 degrees, which is pi/2 radians, I'll get there in a second. We would say, well, that's going to be cosine of 90 degrees, which is 0, negative sine of 90 degrees, which is -1, sine of 90, which is 1, and cosine of 90, which is 0. And if we take that matrix and multiply it by any vector, it should, unless I made an error, I don't think I made an error, but we'll double check here. It should rotate that vector by 90 degrees in the counterclockwise direction. So let's look at an example. Let's say our vector, let's pick a different example. Let's say our vector is the vector, let's make it kind of easy. So the vector is the vector 2, 2. So we're starting by going over 2 and up 2. So there's our vector v. And if I've done things correctly, we would expect for a times v to be the vector that's going to be -2, +2, because it should rotate 90 degrees clockwise. Let's check. So our matrix R pi/2 times v is equal to 0, -1, 1, 0, times the vector 2, 2, reading 0 plus -2. Cool, it's going to work. And 2 plus 0. So here's the matrix, sorry, the vector a times v, which is just left 2 and up 2. And it certainly has rotated it exactly 90 degrees counterclockwise. And someone asked, how would you find the rotation clockwise? You would change where this negative is here. Or alternatively, you could just use the negative angle. So if you wanted to go clockwise 90 degrees, you could say the angle is -90 degrees, which will end up changing the negative from being there to there. So the clockwise rotation is cosine theta, positive sine theta, negative sine theta, cosine theta, which is actually the matrix I did in the previous example. This matrix here was the rotation by pi/6 radians, or 30 degrees in the clockwise direction. So this is all building up to the eigenvalues. Sometimes a matrix changes the direction and not the length of the matrix of the vector it's multiplying. But that's not what we're so interested in. We're actually interested in the other thing that can happen, which is that a matrix can alternatively keep the direction the same and change the length. So here's what I mean. So is there a matrix that when multiplied by a vector only changes the magnitude, but not the direction? Yes, definitely. Here's an example. Here's a matrix A. It's 3, 6, -1, -4. And here's a vector V. It is -6, 1. And if you multiply A times V, you're going to get 3, 6, -1, -4 times -6, 1. You see -18 plus 6 and +6 minus 4 is equal to the vector -12, 2, which is exactly twice the vector we started off with. So what we have here is that A times our vector is equal to 2 times our vector. And this is special. When this happens, we call V equal to -6, 1 in this case, an eigenvector of the matrix A, and the number that it's multiplying it by, or the number that it's stretching its length by, is called the associated eigenvalue. So V is the eigenvector of A, and the associated eigenvalue is lambda equal to 2. And yes, we do use the Greek letter lambda to represent eigenvalues. So here's the question. Are there more eigenvalues of this matrix? Are there more eigenvectors of this matrix? And if so, how do we find them? So the answer to both those questions are yes, there is another eigenvalue and another eigenvector of this matrix. How do we find them? Okay, so here's what we're doing. To find eigenvectors and eigenvalues, words. To find eigenvectors and eigenvalues, we are looking for solutions to the following equation. A times the vector V equal to lambda times the same vector V. And just to be super extra clear here, lambda is the eigenvalue. It's a number or a scalar. And V is the eigenvector. And it's the same there and there. So again, what's special about the eigenvector is that when you multiply the matrix by the eigenvector, you just get a multiple of that same eigenvector. It points in the same direction, and it probably has a different length. Although your eigenvalue could be 1, which would mean it would have the same length, but okay. So to solve this equation, well, let's take a look here. I'm going to do a little bit of rearranging. So we're going to rewrite this as A times the eigenvector minus lambda times the eigenvector equal to the 0 vector, right? Because the A times the eigenvector is a 2x1 vector, and the eigenvalue times the eigenvector is a 2x1 vector. When you subtract two 2x1 vectors, you don't just get the number 0, you get the vector with zeros in each spot. And this is your 0, 0, if we're thinking 2x2, which we are. So then I'm going to fix this because I can't kind of factor out this V just yet. I would like to. So here's what we're going to do. We're going to write this as A times the vector minus lambda times the identity matrix. times the vector. I didn't change anything really, because the identity matrix times V is still just V. That's what's special about the identity matrix. Still equal to the 0 vector. But now on the left-hand side, we're going to factor the V out, and we're going to have A minus lambda I times this vector V equal to the 0 vector. Okay, so you've got something times the vector equal to 0. And there's two sorts of solutions here. You can either have exactly one solution or infinite number of solutions. Those are the only options, right? If you want to, or you could have no solutions, but we don't want to have no solutions. So if we have exactly one solution, not very interesting. Because when you have exactly one solution, it means that your matrix is invertible, right? So if you're trying, so just to kind of rewrite this in a slightly different way, if you're trying to solve B times your vector equal to 0, that's like writing something like 2, 3, 4, 5 times your V1, V2 equal to 0, 0. If this matrix is invertible, which it is, then you're going to get V1, V2 equal to whatever the inverse matrix is times the vector 0, 0. But if you take a 2 by 2 matrix and multiply it by the vector 0, 0, what are you going to get? Yeah, right? There's no choice. No matter what your 2 by 2 matrix is here, thing plus times 0 plus the thing times 0 is 0. The thing times 0 plus the thing times 0 is 0. So it's always going to be 0, 0. So if you have exactly one solution, the solution is that your vector is 0, 0, which is not super interesting. It's called the trivial solution. We don't care about this. In fact, we typically say, or at least I say, that the 0 vector, the vector consisting of all zeros, is not an eigenvector. We don't care about it at all. So that leaves us with the other situation where we have an infinite number of solutions. So we don't want this matrix to be invertible. Right? Because if it's invertible, we have how many solutions? 1. Not invertible, you can either have no solutions or infinite solutions. So here's what we want. We want that this matrix, the matrix, right, and I called it B over here for just a second. We want this matrix, A minus lambda I, to not be invertible. AKA, we want it to be singular. AKA, we want the determinant of this matrix, A minus lambda I, to equal 0. And that is how we start the process of finding the eigenvalues, is by setting the determinant of A minus lambda times the identity matrix equal to 0, and then solving for lambda. You don't have to know all that background, or I should say, you don't have to remember all that background, but I do think it's important that you're aware of like why we're doing this. There's a reason. It's not just like coming out of nowhere that you're taking the determinant of A minus lambda I set equal to 0. There is a reason for it, and this is the reason. So let's look at some examples. Let's look at actually that same matrix we were looking at before. So here's our matrix, A equal to 3, 6, -1, -4. So we're going to take the determinant of A minus lambda I. So I don't want you to write out the long way, but I'm going to write out the long way once. So here's my determinant of A minus lambda times I, which is going to be the determinant of, okay, here's the long way, A, 3, 6, -1, -4, minus lambda times the appropriately sized identity matrix, which is the 2 by 2 identity matrix, 1, 0, 0, 1. Okay, I'm going to do it the real long way, which is kind of annoying. Determinant of 3, 6, -1, -4, still in brackets, James, minus distribute the lambda. You get lambda, 0, 0, lambda. But all this really amounts to, before we take the determinant, is just in each of the diagonal spots, you're going to subtract lambda. That's all you do. You shouldn't do any of this. You should just say it's going to equal the determinant of the matrix 3 minus lambda, 6 minus 0, -1 minus 0, -4 minus lambda. Or in other words, take your original matrix A, subtract lambda in each of the diagonal spots, and then do the determinant. And by the way, just to make sure everyone's clear, when I say diagonal spots, whenever we say the diagonal of a matrix, we mean the entries starting in the upper left corner going down to the lower right corner, or all the entries where the row and column are the same number. The entry in the first row, first column, second row, second column. And if there was a more, the third row, third column, etc. And now we're going to find this determinant. It's going to be equal to 3 minus lambda times -4 minus lambda minus 6 times -1. And we're going to set that equal to 0. Because of what we said on the previous page. And then the hope is that things turn out nice. Things factor, but we should multiply. Oh. If that's 0 right there, it's not here, I know. But if like one of those two numbers is 0, and that part just goes away, don't multiply this out. It's already factored for you. You already have your solutions if that's 0 over there. So be smart about this. Don't do more work than you have to do. But it's not 0 there, so we do have to multiply it out. So multiplying it out, we get 3 times -4, and then -3 lambda, and then plus 4 lambda, and then minus lambda times minus lambda is plus lambda squared, plus 6 equal to 0. Keeping everything on the left-hand side, I'm going to write this as lambda squared, minus 3 lambda plus 4 lambda is plus lambda, and -12 plus 6 is -6 equal to 0. Much of the time, this will factor. But if it doesn't factor, then you do need to use the quadratic formula. And that will happen in 17C for sure. It might happen in this class as well, but definitely in 17C, when you find eigenvalues, sometimes they're going to be not nice. So factoring here, we get lambda plus 3 times lambda minus 2 equal to 0. So the eigenvalues are, in no particular order, lambda 1 equal to +2, and lambda 2 equal to -3. We typically call them lambda 1 and lambda 2. If you had to pick which one to call lambda 1, I would pick the bigger one to be lambda 1. So if they're both positive, the bigger one is lambda 1. If one's positive, one's negative, the positive one's lambda 1. If they're both negative, it doesn't really matter. It doesn't really matter at all, actually. You can call them whatever you want. But this is the typical naming. So after you found the eigenvalues, and you're always finding the eigenvalues first before you start finding the eigenvectors, then we can go back and try to find the eigenvectors. So for lambda 1 equal to 2, we already found it, or we already saw what it was before, but here's how you would find it. So you're trying to solve A times the eigenvector that we don't know equal to lambda 1 times the eigenvector that we don't know. And usually if you're calling it lambda 1, you should call it V1. So we're trying to figure out what V1 is. Let's write this out as an actual equation. So our matrix is still the same, still the matrix 3, 6, -1, -4. I don't know what the eigenvector V1 is. That's what I'm trying to find. So I'm going to write it as the 2x1 vector, and usually we call the elements of it X and Y. You can call it really anything you want, A and B, U and V, but X and Y is pretty typical, and I'll talk about Y once we find it. And then lambda 1 is 2, and then again, X, Y. When you do it this way, so let me back up. This is a matrix equation. It's representative of a system of 2 equations and 2 unknowns. You almost only ever need to write down one of the equations. So the first equation, just looking at the top row, is 3 times x plus 6 times y equals 2 times x. Cool. I usually like to get all the y's on one side and all the x's on the other side. So I'm going to rewrite this as 6y equal to 2x minus 3x is -x. And honestly, I would stop there. Now you get to make a choice. Pick any number you want. Back up. Pick any non-zero number you want for either x or y. I'm going to pick y equal to 1. If y equals 1, what does x have to be? Well, y equals 1. 6 times 1 is 6. If negative x equals 6, then x has to be negative 6. So here's my eigenvector. My eigenvector is the vector x is negative 6, y is positive 1. That is one of a literal infinite number of choices that would be correct. You could have picked 12 and negative 2, or 1 and negative 1, 6, or anything that is a multiple of this vector. So any non-zero multiple of an eigenvector is also an eigenvector for that same eigenvalue. So I just want to point out, you could have picked something like silly, like, I don't know, 300 comma negative 50. That's also an eigenvector for this eigenvalue. The standard or typical choice is the choice where the entries x and y are the smallest possible integers. So we would prefer not to have fractions, but we would like to not use numbers bigger than we need to. So this is, you would either see this choice or the choice 6, negative 1 as the vector here, as the eigenvector. I will mention as well that if we had written down the second equation, which I don't really have room for, let's go down here. So if we looked at the second equation, which would have been negative 1 times x plus negative 4 times y equal to 2 times y. And then we add 4y to the other side, we still get the same relationship. Negative x equal to 6y, and then you can pick y equal to 1 and get x equal to negative 6. Both equations should give you the same results with, excuse me, sometimes there's a rare exception where one equation doesn't help you and then the other equation just gives you what you need. But the equations will never disagree with each other. They will always give you the same, or one of them will just be not informational at all. So in this case, we'd say for lambda 1 equal to 2, the eigenvector v1 is the vector negative 6, 1. And just to go back to verify, if you take that matrix and multiply by negative 6, 1, it is, we actually already saw, but 3, 6, negative 1, negative 4 times the vector negative 6, 1 is going to give us negative 18 plus 6, which is negative 12, and positive 6 minus 4, which is positive 2, which is exactly the eigenvalue times the eigenvector, as it should be. Let's find the other one. So we did it for lambda 1 equal to 2. Now let's do it for lambda 2 equal to negative 3. So I'm a fan of this process where you are trying to solve a times your eigenvector equal to lambda times your eigenvector. I'm going to do this one two different ways, just so you can see it another way. So if I was doing this again here, I would say, okay, great. I have my matrix 3, 6, negative 1, negative 4 times my eigenvector, which I'm trying to find, equal to, in this case, negative 3 times my eigenvector that I'm trying to find. Again, we typically only need the first equation. So I'm going to say 3 times x plus 6 times y equals negative 3x. I'm going to subtract 3x from both sides and get 6y equal to negative 6x. I do recommend dividing both sides until you have the smallest integers you have. So in the previous example, I didn't divide both sides by anything because the coefficient of x was 1 or negative 1. Here, I would divide both sides by 6 and say y equals negative x. And then I would pick x equal to 1 and get y equal to negative 1. So my eigenvector is going to be 1, negative 1. Or negative 1, 1. Or 3, negative 3. Or 5, negative 5. Or negative 6, 6. Or literally any non-zero multiple of this vector is also an eigenvector. That is a valid, correct answer. Or we could do it a different way. So I want to point out, I like doing it this way because I think it evokes the meaning of eigenvectors and eigenvalues. Oh yeah, you're supposed to get the matrix times the vector equals the eigenvalue times the vector. That's where we started when we were doing this whole thing. But you could also solve it by saying, I want to try to solve a minus lambda I times the eigenvector should equal the zero vector, because that's another intermediate equation that we saw in this process. If you do it this way, it'll also work out the same. Let me show you. So here we would have 3 minus, let's see, the eigenvalue is -3, so it's going to be 3 minus -3, and then 6, and then -1, and then -4 minus -3. Because again, you're subtracting the eigenvalues on the diagonal, nowhere else, times the eigenvector that we're pretending like we're trying to find, now equal to the zero vector. So here's what we've got. We've got 6, 6, -1, -1 times x, y equal to 0, 0. And if you use either equation, well, the first equation is 6x plus 6y equal to 0. And yeah, we're getting exactly back to the same place. That's 6y equals -6x, which is y equals -x, which gives you the same eigenvector. Here's my thoughts on this. I like this better. But if your eigenvalues are not pretty, if they are not integers, meaning they're either irrational, like you've got some sort of 1 plus or minus the square root of 3, or even imaginary, which they will be in 17C, doing it this way is usually algebraically easier. And we'll definitely talk about that when we do 17C. Okay, so we got good 13 minutes here. Couple things to say. So typically, square matrix, a 2 by 2 matrix will have 2 eigenvalues. A 3 by 3 matrix will have 3 eigenvalues, and so on and so on. You can get the same eigenvalue repeated. So it could happen that the 2 by 2 matrix has the eigenvalue like lambda equal to 5 twice. It doesn't typically happen though. There was something else I really wanted to make sure I mentioned here. Oh, I know what it was. Okay, cool. Let's look at an example that's kind of funky, but perfectly fine. So let's say we want to find the eigenvalues and eigenvectors for the following matrix. A equal to, sure, 2, 0, 5, -3. And I'm gonna let you all do that quickly because I really have to pee, but I don't want to end class right now. So find those eigenvalues. They should be not hard to find. I'll write it down. hopefully these eigenvalues were extra easy to find because there's a 0 right there or right there. Because when we find the determinant of a minus lambda I, which is going to be the determinant of 2 minus lambda, 0, 5, negative 3 minus lambda, which is going to be 2 minus lambda times negative 3 minus lambda minus 0 times 5, set that equal to 0. That's 0. There's no need to factor here. You've got 2 minus lambda times negative 3 minus lambda equal to 0. Your eigenvalues are lambda 1 equal to positive 2 and lambda 2 equal to negative 3. Coincidentally, I happen to pick numbers that are the same eigenvalues as the previous example. That is just a coincidence. There's no reason they should normally be 2 and negative 3. I just was making something up on the fly. So, useful fact. If you have a matrix that is lower triangular or upper triangular, the eigenvalues are literally just the diagonal entries. So I could also point out that if someone gave us a larger matrix, which we usually don't have the tools to find the eigenvalues of, if someone said your matrix was B equal to, say, 3, 1, 5, 0, 9, 2, 0, 0, negative 7, it is very, very true that the eigenvalues of this matrix are lambda 1 equal to 3, lambda 2 equal to 9, and lambda 3 equal to negative 7. And that is always true for an upper triangular or a lower triangular matrix, that the diagonal entries are the eigenvalues. It's kind of great. So the real point here is that if you see a matrix like this, you don't have to do the work of finding the eigenvalues. It is accepted that you can just say, yeah, I know the eigenvalues are 2 and negative 3 here. Well, let's find the eigenvectors, because there's kind of a slight funkiness in finding the eigenvectors for matrices that are upper or lower triangular, at least for one of them. I don't remember which one it is, so let's just do both. So for lambda 1 equal to 2, we're going to do a times v equal to lambda 1 times v1. Sorry, I should have said v1. That's going to be 2, 0, 5, negative 3 times the vector we're trying to find equal to the eigenvalue times the vector we're trying to find. So here's the first equation, and this is an example of where the first equation doesn't help us. The first equation is 2x plus 0y equals 2x. And while it's certainly true that 2x is equal to 2x, it doesn't tell you anything. X could be anything, and that would always be true. So that doesn't help us. So sometimes one of the equations won't help you. And then you go to the other one. The other equation is going to be 5x minus 3y equals 2y. And this one does help us. We get 5x equal to 5y. We get x equal to y. So the eigenvector here that I would pick would be the vector 1, 1. I know what I was going to say. I should also point out another terminology thing is that the line here, y equal to x, is called the eigenline. So the eigenvector is the vector 1, 1, but this line, y equal to x, is the eigenline. And what that really just means is that if you were to draw a vector that started at the origin and ended anywhere on this line, it would be an eigenvector. I would pick the vector 1, 1, but you could pick the vector 3, 3, and you could pick the vector negative 4, negative 4. All those would be eigenvectors because they all are on the eigenline. Okay, let's find the other one because it is interesting. So for the second eigenvalue, lambda 2 equal to negative 3, we have the matrix 2 times 0, James, 2, 0, 5, negative 3 times the eigenvector we're trying to find equal to negative 3 times the eigenvector we're trying to find. And again, this is just your matrix A times your unknown eigenvector v2 equal to your eigenvalue times your unknown eigenvector. Okay. So now here's where things get a little bit weird, I think. First equation is 2 times x plus 0 times y equals negative 3 times x. So if 2x equals negative 3x, what's x have to be? 0 is the only choice, right? Any other number doesn't work. 2 times something that isn't 0 doesn't ever equal negative 3 times the same something that isn't 0. Or if you prefer, you could add 3x to both sides and say 5x equals 0, so x has to equal 0. And you might feel like we need to use the other equation. That's actually not true, but let's do it anyway just to see what happens if we do. So if you use the other equation, you get 5x minus 3y equal to negative 3y. The negative 3y is cancel, and you get 5x equal to 0, again giving us x equal to 0. Well, shoot, what's y? Well, what isn't y? What's the only thing we said couldn't be an eigenvector? So if x is 0, my eigenvector is 0, comma, not 0. But here's the good news. Any non-zero choice is correct. Because if you pick 0, 1, and you pick 0, 3, and you pick 0, 5, and you pick 0, 6, and I pick 0, 7, and you pick 0, negative 4, all those vectors point in the same direction. All those vectors are on the same eigenline. So it doesn't matter if you pick 1, 2, 3, 4, or 7, as long as you don't pick 0. Or in other words, if you are finding an eigenvector and one of the coordinates of the eigenvector is 0, the other one is typically 1 is the choice we make. Although you can pick anything, but usually we pick 1. So our second eigenvector is 0, 1. And it's true, right? If you actually do the multiplication, 2, 0, 5, negative 3 times 0, 1 is equal to 0 plus 0 and 0 plus negative 3, which is exactly negative 3 times the eigenvector. Check. It works. It would also work if you pick 0, 7. Because again, all these vectors that have a 0 in the x direction and a non-zero in the y direction, all those vectors point straight up, whether it's 0, 1 or 0, 2, 0, 7. All those vectors are pointing in the same direction, which means all of them are equally good eigenvectors. Let's see, we got a couple minutes left. There's one last thing I wanted to say. I do have an example of this somewhere, I know. Yeah. So typically you won't be asked to find eigenvalues and or eigenvectors of larger matrices, but someone could ask, where'd you go? There, yeah. So here's a question that I think is a decent question to test knowledge. So here's the question. Is the vector 1, 0, 1 an eigenvector of the matrix negative 3, negative 1, 5, negative 2, 1, 2, negative 2, negative 1, 4? Even if this was a smaller matrix that we knew how to find the eigenvectors of, like a 2 by 2, you shouldn't do this by finding the eigenvectors. The way you test to see if something is an eigenvector is you say, well, if I multiply the matrix by the eigenvector, do I end up getting a straight multiple of it? Well, let's check. If I call this V, call this A. It's perfectly fine if you're just given vectors and matrices to just give them whatever names you want to give them. It is a standard kind of thing. So let's see, if I get A times V, it's going to be negative 3, negative 1, 5, negative 2, 1, 2, negative 2, negative 1, 4, times 1, 0, 1. So I'm going to get, let's see here, negative 3 plus 0 plus 5 is 2. Negative 2 plus 0 plus 2 is 0. And negative 2 plus 0 plus 4 is 2. And that's really kind of funny because I just guessed that one. I didn't actually mean for that to come out to be an eigenvector, but it is. Why is it an eigenvector? Because it's exactly equal to 2 times or some number times the original vector. So yes, it is. So if your matrix times whatever the supposed eigenvector is equal to a multiple of that eigenvector, it could even be 0 times the eigenvector. 0 can be an eigenvalue, then it's an eigenvector. So yeah, V is an eigenvector. Kind of funny. I didn't mean to pick it. I just literally made one up and it happened to come out that way. That is surprising to me, but it happened. So that is the long and short of eigenvalues and eigenvectors. As far as the rest of the week, you'll have class on Wednesday. That's your last 17B class. And there's no class on Friday. We meet on Thursday. I'm guessing well, at least in Dell's class, he's probably going to talk about iterated matrix multiplication, which it is what it is. That's probably what he's going to. So if he doesn't talk about that, let me know. Otherwise, we will talk about that on Thursday because it is a bit complicated. And then there's no class on Friday. So Friday is the first day of finals. Some of you might have a final on Friday. You might want to double check just to make sure. But there is no class on Friday. Question. Oh, sorry. I'm considering the possibility of holding a review. I'm thinking either all of you have your finals on Thursday, I believe, right? Whether you're in Dell or Temergaliava's class. So as far as office hours, we'll be having drop-in hours on Friday and the rest of the week. And those are on our website, I think, but they'll all be in the library in Shields. I'll be there Friday. I'm only there from 10 to 11 because that's some appointments I have to go to. But the following week, I'll be there every day from like 10 to noon and 1 to 3. And Grant will be there too. And then I think I'm going to try and do a review. I have to check my schedule first, either on Tuesday or Wednesday from like 4 to 6, so maybe 3:30 to 5:30. Maybe I'll put like a poll in Canvas to see if there's a day that's better for people versus the other day. Either way, I'll record it and post it. So if you can't come in person, you can certainly come via Zoom or watch it later. But I imagine you might all prefer to come in person. So I will try to pick the time that's best for everybody. That's all I got.